The Comet Interceptor mission actually states that the target will be either an interstellar object or a comet. It will be a flyby, meaning we just fly very close to it and then that's it. So we have to maximize that moment because that's the only thing we are going to have. Comets are the remnants of what were the building block of planets.
I'm learning a lot of things, Dr. Ino.
The entire lifetime of the spacecraft is 5 years. How long it will be actually there depends on when the right target will show up. We don't know yet the answer.
So I am very pleased to have with me today Dr. Laura Ino. Tell us a little bit about the Rosetta mission and then maybe lead into this Comet Interceptor project.
Sure. So Rosetta was, I think, is one of the most famous missions from ESA, the European Space Agency. And it was amazing because it broke so many, it did so many firsts. Like it was the first probe to actually stay hibernated in space for 10 years. And also the first spacecraft to orbit around the Comet 67P, which is also a given name, but for me it's really hard to pronounce. I'm not going to say the name. And so this mission was really, really important because by orbiting for 2 years around the comet, the spacecraft really collected so much data, and we are still working on it, even though the mission ended already in 2014. Yes, it's 10 years now. No, I think it's 2016.
So basically, it started orbiting 2006. He started orbiting around,
right, exactly.
This comet.
Yeah.
And approximately where was this comet in our solar system?
So the comet was approaching the sun, so it was a returning comet. So this is how we call comets that have periodic orbit. So this comet comes around every about 6.5 years. And the reason why the first mission to a comet, well, there were other missions to comets before, but this was the first one in which you had a spacecraft actually orbiting the comet. And because it was very challenging, then it was, and also because of the window launch, because also when you launch the spacecraft will also determine which kind of object will be accessible. So because of all of that, this comet was chosen, and also because being a returning comet, the orbit was known very, very well. So it was possible to plan the mission with great accuracy, and the spacecraft even had a little bit of gravitational push thanks to Jupiter. So it went really far away in the solar system. So it was kind of impressive. And then it even, so the other impressive things, which it was also a first, is that Rosetta carried a lander, which was called the Philae. And the lander was supposed to land on the comet. So it was left from the main spacecraft, but because of a little bit of technical problem, and actually didn't land smoothly as it was supposed to do, but was bouncing. So it bounced because these comets are minor bodies of the solar system, and so they have more, let's say, much weaker gravitational fields with respect to planets. So because of the weak gravitational field, the lander wasn't able to stick on the place, but it was bouncing around. So it bounced 2 times, and the contact between the lander and the spacecraft was actually lost for a little bit. So it was really a very thrilling mission for a lot of reasons. And then at the end, they found the position of the lander on one image of the comet. So it was very unlikely because it went in like, let's say, like in a ravine.
A ravine, okay.
That, yes, that was very...
It got stuck in a ravine.
Yeah, and it was also in the shadows, so it couldn't refuel, but it was also upside down, so it couldn't really fuel itself. So it was able
Meaning like it was powered by the sun, but if it's upside down, it can't get to the sun.
exactly.
Okay.
So it was able to send a little bit of the data that were collected, but then after I think maybe 1 or 2 days, it was done.
You know, it's amazing. There's these like for me, I'm new to this area of space exploration. Like I when I was growing up, I had a fascination with space, but then I had my career and I was, became a professional. I just lost track and I had no idea these sorts of projects were ongoing and that there's a man-made thing circling a comet for a decade. I didn't even know this, you know? So it's quite amazing.
So circling around the comet was for 2 years, but the spacecraft was hibernated for 10 years during the trip.
Oh, I get it. I get it. Okay. So basically it was on its journey for about 10 years before it reached the comet and then circled the comet for 2 years, you said. Okay. Including trying to put a lander on the comet itself.
Exactly. And so when also the spacecraft had almost finished all the energy, it couldn't provide any more information because it wasn't going to be able to communicate anymore, then it was decided to let the spacecraft also go on the surface of the comet. So in a way to join the long.
A final resting place, I guess.
Okay. So basically, the idea is that comets are the remnants of what were the building block of planets. Okay, so in some way, comets are like fossil. We are used to fossil on Earth. They tell us what what animal were going around thousands of millions of years ago. For comets, it's kind of the same. So they tell us what was the nature of this building block. So because and in particular, what we want to study now, that was the point that I wanted to make, is a comet that comes from very far away in the solar system, in a region which is called the Oort region, the Oort cloud. So this is really the farthest, the most far region in the solar system, and that's where we believe all the remnants of the planetesimal disk from which the planets formed are still located.
Okay.
Okay, so basically the story is the sun formed. What is left from the original nebula is collapsed in a disk, and then the disk, this disk, which is called the planetary disk, is the region where the planets formed. Okay, so we know that in the inner region, all the rocky planets were formed. In the outer region, all the giant gas planets are formed. And even outside of that, there is the Oort cloud. That's where the original, what are called planetesimals, so these tiny blocks that formed the planets, they stayed there basically unaltered. They weren't able to form a planet. They just stay there. And then the idea is that when there is a perturbation, like a star close to the sun is coming closer, or some gravitational waves, or some kind of instability, one of these objects is pulled towards the inner part of the system and becomes a long period comet. So if we look at this object, we can understand what was the original formation of the protoplanetary disk.
Okay. I understand now. So basically these are it's of the same basic building block material that our planets were formed from.
Right. How water was delivered on the Earth's surface is one of the biggest questions. We have asked the question for a very long time. Since we understood how planet forms, then we knew that the condition on on the surface of the Earth at the time of its formation was the temperature was so high that there was no way that you would have volatiles around, you would condensate water there, right? So the water has to come from some other place, or there are also some theories that say that water was inside, and with time it was able to come outside. So like there is one theory that claims the water comes from other bodies, and one theory that says that actually it was from the Earth itself. So
How would it come from other bodies? I don't understand how it would come from other bodies.
well, I mean, we know that a lot of things came from other bodies. Like we know that organics compounds they came from asteroids. So we just found it was news on the news, I think 1 month ago, on the Bennu asteroid. There was some sample returning mission, and they found that it was rich of organic molecules. And we know that the Earth must have been highly bombarded by these bodies in the early times. How do we know? Because first of all, we have the moon, and the moon we know that has been formed by an impact with a planet very similar to the Earth. And then also, and after the formation of the moon, you can see on the surface.
Just so I want to repeat it so everyone understands. So basically, the moon itself is a product of a collision between Earth way long time ago and another object. So we know other objects have hit Earth. Big objects have hit Earth before because the moon is evidence that something really big hit the Earth to be able to create a chunk as big as the moon.
We don't have like the final proof of that. This is one of the theories of the formation of the moon, but there are some evidence for that. Like, for instance, it's actually very similar to the Earth from the point of composition. And that's hard to explain if it's something we capture it later on.
I see. It's hard to explain if it's just a rock that got attracted by the Earth's gravity. You know, it's a pretty big rock, I guess.
Yeah, exactly. It's pretty big with compared to Earth, and also, I mean, we can look at the surface of the moon or even of Mercury, you know, and it's full of craters. So we know there have been a lot of impacts.
A lot of impact, yeah.
Yeah, on Earth we don't see as much because we had erosion and all the phenomena that covered.
So the organic material on the Earth could have come from these asteroids hitting the Earth, hitting the Earth. And actually, this is pretty well accepted in your community that yes, this is how we got a lot of our organic material actually from space.
Yeah.
Okay. All right. I'm learning a lot of things, Dr. Ino. And so how about water? I don't quite understand. I mean, it just seems like, are you saying somehow that created some reaction that created the oceans here? Or because clearly there's a lot of water here on the Earth. It's not volume wise, we're not getting it from another body. Is it started some sort of chain reaction? Like help me understand that.
No, it's really it's literally carrying the ice. So
I get it. Okay.
Basically, it's like they were our ice stuck in the fridge, and they at some point they just came closer and they collapsed on the Earth, and then the ice melted.
It's like an iceberg, like basically a huge iceberg could have, in the form of a huge, like a comet, I guess, a huge comet iceberg slammed into the Earth, and that gave us the water.
Yeah, basically that. So until 30 years ago, this is what we thought comets were, like big ice block with some dirt in it that were able to carry a lot of ice and bring it to the Earth.
I see. Because the idea that somehow water created on the Earth, you're saying that because it went through this period of where the Earth was very hot, all of the water would have evaporated.
Yeah.
So it's like it needed to have come after the Earth was formed through this very hot period, and it's very hard to kind of come up with a hypothesis on how that happened. And one of them is that we got our water from out there, that it, like this big comet crashed in, ice comet crashed in, and that gave us our water. I mean, what you're sharing with me, can you believe that I went through an entire primary education, secondary education? I went to a prestigious university. I didn't know this. I didn't know this. I mean, I didn't know this until this moment. And it wasn't even, this wasn't even the topic of our conversation. So thank you for, I don't know, enlightening me. It's deeply fascinating. I had no idea that this is a hypothesis out there. And now I'm much more educated on why we're interested in comets. Before it just seemed like a really cool thing to do and a very hard thing to do. And more the engineer in me was interested in how do you intercept this very high velocity object. And now you've kind of sparked more of the scientist in me, like, oh, these are the interesting questions we're trying to answer. Okay, so now, now, now bring us from the Rosetta project to the Comet Interceptor project.
Yeah, so I mean, after Rosetta results, first of all, we understood that actually comets are not snow. Like the whole definition was like snowball, dirty snowballs. So with Rosetta,
Dirty snowballs. Okay, all right.
but Rosetta, we understood it was actually the other way around. So the surface of the comet is actually very dark and very solid. I don't know how to say it. I mean, like a crust. Okay. And also the quantity of ice was not, it was not like that. So it was not the kind of model, but it was more like an agglomerate of small constituents in which you also find ice. So it was like what the minimal constituents are called pebbles.
So basically, you're saying the comet is mostly like solid matter.
Yeah.
But then on the surface is more the water or the ice.
No. Sorry. No, I'm saying that we thought it was just mostly ice and just a little bit of rock. Instead, it's more like the other way around. So the crust is actually dark and solid, and the inner part we can look at that directly, right? But we understood. So the model, at least the model that has been developed within my group, that also explain a lot of the evidence we saw, is that the inner part of the comet is made of little constituents called pebbles. So basically, the inner is very, very porous.
Porous, yes, sure.
Yes, exactly. Okay, so the 67P comet will float if you put it in your ocean.
Okay, so it's very porous,
like a rubber duck.
Okay.
So it's like a rubber structure. Okay.
Okay.
And within this porous, you also have ice.
Ah, okay, I understand now. Okay. So it's almost like it's like if I'm picturing like a sponge, but inside each of the empty spaces of the sponge is ice.
Mm-hmm. Right.
Okay. And
that the sponge doesn't have a crust, so you have to, and you picture this sponge like within a pot.
I see.
So what happens when the comet comes close to the sun, then the inside of the pot will start to heat. Not boil, because there is the cover of the pot.
The cover, okay. So it just heats up.
So it heats up and then it sublimates directly because there is high pressure.
It sublimates, turns directly into gas, you mean?
Exactly. It turns to gas and tries to go out. And when it goes out, because the gravity on the surface is very, very low, it drags part of the dust with it.
It shoots out part of the dust.
Yeah, exactly. So the vapor the gas will escape from the surface of the comet, and it will also rapture a little bit of the dust on the surface, which will also go out. Because actually what we see, the brightness of the comet, it comes from the dust tail. Most of it.
Yes. Oh, I see. Very interesting. But wouldn't that change the trajectory of the comet? Like all this thing exploding and
It can
you
happen.
know,
So there are comets who undergo outburst. So when they have so much of this suddenly that and even they can fragment, so they can break, or they can also change the trajectory because of this pulse.
uh-huh. But typically not. Typically, there's enough like the mass and the effect the gravity has on the mass keeps the trajectory pretty consistent. That's why we can predict these orbits. Is that why?
So the fun part about comets is that typically doesn't. So, I mean, like they are usually considered the cut of the space because they have tails and because they are unpredictable. so,
Okay.
so yeah, I mean, like a lot.
No, hold on. The cats of space because they have tails and they're unpredictable.
Yeah,
Okay.
and yeah. So well, so a lot depends on the mass, initial mass of the nucleus of the comet. So the comets I'm referring to, they usually have bigger nucleus. So
Okay. So bigger mass means a more consistent like trajectory, whereas smaller means that these outgassing could change the trajectory.
what I meant is bigger nucleus can be more stable because the gravity is larger, so they can they can be more consistent. Like yeah.
Okay. So bring us back to Rosetta to the comet interceptor. Yeah.
Basically, the idea is that if you want to understand really if comets are the one who were able to provide the ice, to bring the ice, we need to look at pristine comets. So comets that are more primordial, that have been less altered by the approaches close to the sun.
Oh, I see. I see. Because if it's an older comet, it's been orbiting the sun a long time, and that may have changed a lot of its characteristic and material. And so you want to get a comet that was more.
That is coming from the Oort cloud to the inner solar system for the very first time.
So one of the big changes then I'm hearing for this comet interceptor is that you have a much better idea of the kind of comet you want to intercept. A much Are we going to be doing it the same way, or is there some advancement in the technique of how the intercept is going to happen?
So no, it's not in the same way. First of all, because the target is a comet that is on a very different orbit because it's going to be coming very fast and it's not going to come back. So it's a fast object by definition, basically. So we can't make any orbit around. So it will be a flyby, meaning we just fly very close to it and then that's it. So we have to maximize that moment because that's the only thing we are going to have. So we will approach the target and then we will be gone.
So how has that changed the technique again to how we intercept it?
First of all, we don't know the target yet. And once we observe the target, we have to find out the orbit, right? So it's not like a comet that we already know, for which we already have all the details, so we can predict the position at any time exactly. This is something that we have to find out after the discovery. So we can't plan with great advance the encounter between the spacecraft and the target. This will be done after we find the target. And again, because the object is coming very fast and the spacecraft also will be going fast, so it will the encounter will have very high relative velocity. So that's why there will be no possibility to orbit or to look at it for a long time because we will not be able to follow it, right? So that's why it's completely different from the technical point of view. That's an interceptor and not an orbiter.
I see. It's a so okay. So that's a one big difference. It's we're intercepting versus orbiting, hence the name Comet Interceptor. But is it like a quick flyby like this, or are we going to try to match its match its velocity and be in parallel for a while, or is it going to be really just kind of crossing like that?
It's going to be very fast. So crossing like that. But of course, we will start to take data as soon as we start to see it. So we are going to start collect the data as soon as the spacecraft has a sight of it. So and then we will collect the data all through the time of the flyby. And also, so the idea for try to maximize the science return is to have a multi-probe spacecraft. So we have one main spacecraft, which is called Spacecraft A, and then two other spacecraft that are that will fly together with the main one, and then will separate once it approaches the target. So we will have three different point of view. Okay, because there will be Spacecraft A that is the only one that talks to Earth, and then there will be the B1 and B2 spacecraft. So we will be able to collect the information from three different points of view. And the idea is that this will allow us to get a 3D view
Oh, wow.
of the
Great. A
comet.
3D picture of the comet. So does B1 and B2 communicate with A, and then A relays the information back to?
Yeah, exactly.
Okay. And the most interesting thing is that, I did a little bit of reading on the Comet Interceptor, is that the interceptor is actually going to be stationed in a very interesting point first, before, like, as it's waiting for, I guess, you to identify what it's going to go after or target. So help us understand that, like, that process of where you're going to locate the spacecraft, or like you're going to hitch a ride on a rocket. Where's the rocket going to take you to?
Yeah, so the spacecraft will be parked in this L2 point, which is actually the same place where JWST is also the Webb telescope is also located. So that's a point where
but the L2 just the L stands for Lagrange, or like, okay. So tell us about this Lagrange point and what's unique about the Lagrange point.
So for the Lagrangian point 2, there are a lot of advantages. So first of all, it's stable. So it's a point that is located a little bit far away from Earth, so 1.5 million kilometers from Earth. So it's farther than the moon, and it's on the other side of the sun. So the sun is here, the Earth is here, the moon is here, and it's, of course, orbiting the Earth. And then there is the L2. And because it's very stable from the gravitational point of view, the spacecraft has to consume a minimum amount of fuel or propulsion to just stay there. And also, because it's on the opposite side of the sun, also is not very hot. So it's also the thermal conditions are also good. So that's a good place where the spacecraft can just wait.
So if I could picture this in 3D space, it's like the sun, the Earth, and then the Lagrange point.
Yeah.
Okay. And this Lagrange point, my layman's understanding is it's a point where the gravity of, so basically the pull of the Earth and the pull of the sun are balanced out or cancel each other out. That's why it requires very little fuel to be in that spot. So it's a very efficient, I guess, a very efficient place to just park yourself. And you said the Webb telescope is there as well?
Yeah.
The first step is to hitch a ride on a rocket that will get it to the Lagrange point. It's going to hover there or just park itself there in orbit, trying not to spend very much fuel. How long do you expect it to be parked there? Or is it only going to be parked there very briefly before it needs to go intercept an object? And is there an envelope, like you expected to be parked from 0 to X number of years.
Yeah, so exactly the last one. So so the idea is to build the spacecraft in a way that it will be able to wait up to 3 years.
Okay, up to 3 years. Okay.
The entire lifetime of the spacecraft is 5 years.
Okay.
So there is a little bit, of play between these years, but the idea is that it will be 3 years parking, up to 3 years. Of course, how long it will be actually there depends on when the right target will show up. We don't know yet the answer.
And so does that mean if the lifetime of the spacecraft is 5 years, does it mean you're budgeting like if you have to use up all 3 years to wait for the perfect target, does it mean that you have 2 years to reach the target? Is that something like that? Or how long do you anticipate reaching the target?
Yeah, we can have up to 2 years to reach the target. Exactly.
Okay.
Yeah.
All right. And help me understand where this target could be. Like, where in our solar system could this thing reach?
Closer to the Earth is would be better, but it can go between Mercury and Mars. Yes, it can. It couldn't go farther than that.
Okay, all right. That gives us a way to picture this.
Think that this comet is not on this plane, right? It will be in space, so you have to think of distance not like on this plane, but three-dimensional, so like in a triangle. So even if you think about Mars distance, right? But it will be here, right? Because it will be the distance with respect to the height, the height with respect to the ecliptic plane. Okay.
Yep. I understand. Yeah. So, okay. Then this target identification process. So, yeah, tell us a little bit about how the Rubin telescope fits into this, because I had the pleasure of talking with Dr. Greenstreet, who works at the Rubin Observatory, and I believe she's part of a group that looks at interstellar objects. So tell me about the partnership or how the collaboration, and are you, this idea of target selection or target identification, which telescope projects do you work with? Is that the main one, or are there many? Like, just give us a little bit of an understanding of that process.
Sure. So I am a member of a working group, which is called a Target Identification Working Group, which was appointed by ESA, and our main task is to come out to answer all the questions you just asked. So until a few years ago, let's say, the discovery of these comets was almost always serendipity. I have another Netflix reference. I don't know if you saw the Don't Look Up movie, but I guess you saw that. No, you didn't.
I have not seen that yet.
But it's with Leo DiCaprio and Jennifer Lawrence.
Okay, I'll put it in my queue.
So in that movie, the story is about discovering by chance a comet, and then the comet is actually approaching the Earth and it will destroy. Oh, I shouldn't spoil it. Anyway.
Okay.
And that was actually very realistic because that was what happened, except the destruction part, with the Neowise comet, which was discovered during COVID. It was discovered like serendipity, and then only 3 months before it approached perihelion, so the closest distance to the sun. So these kind of objects in the past have been always discovered very late on, so just before they reached us. And of course, this won't be a big issue for Comet Interceptor because we will not have the time to assess the target and decide if that's a good one or not. So we really hope that we are going to do better. And this is a hope that actually has some real possibilities, real chances because of the Rubin Observatory. So if you already talked about that, but just to mention it again, so the Vera Rubin Observatory is in Cerro Basón in Chile, is under construction, but it's going to be completed very, very soon. And it's going to carry out a survey of the southern sky, which is called a Legacy Survey of Space and Time, LSST. And what is new about this observatory is about this survey, this project, is that it's going to be to look at the sky continuously. So it will be run by an algorithm. So that will decide which part of the sky should be looked at and in which band. And then we'll move to the next part of the sky. But it will be so fast and with such a large field of view that it will be able to map the entire southern sky every 3 nights. So we will have basically continuous monitoring of the southern sky, which means, and with also the capability of a telescope of 8 meters of diameter, so like the biggest telescope in the world. So this means that we are going to see very faint objects. So the idea is that because of the time cadence of the observation and because of the sensibility, this telescope, this survey will be able to find these comets much earlier on than what we have done until now. So we should go from 3 comets per month, if we're lucky. No, sorry, 3 comets per year, basically, like last year, to 3 comets per night. So this is going to be
wow. Okay.
change in the game. So the reason why we believe that even the target for the Comet Interceptor mission is going to be detected by Rubin is because it's going to be the most the best well-suited observatory to do this kind of discoveries. And discovery will be actually public every 60 in an alert 60 seconds after. So
instantaneous.
Yeah, basically instantaneously. So you asked if there is some collaboration. So not formally, okay, but that's between ESA and Vera Rubin, also because the LSST project is an American project funded by NSF. So it's a completely different, it has its own story and motivation and strategy and everything. While this is an ESA mission, so it's a European mission, but we don't need a formal agreement because anyway, all the alerts will be immediately public.
I understand. So basically, the Rubin, the data is available. So basically, you'll be leveraging that data to help with your target selection.
Only the discovery will be public. If you want, only the alerts. So only the discovery data will be public. Everything else will not be public. So, but what we need is to see, okay, there is these objects there in the sky. And then because it will be found so much earlier on, we will be able to follow up observation with other telescopes.
But you're saying the discovery data is what you need.
Yeah.
And that will be public. And the reason why the Rubin is special is because it's able to see faint objects, which means you'll be able to see them when they're very far away, which gives you time to plan the mission if you find a suitable object.
Right. Time to plan the mission, and before that, to plan follow-up observation, because we need to understand the nature of the comets. Right. We need to determine if it's new incoming comet or if it's not. If it has all the kind of parameters that we need in order for obtain the optimal science return from the instrument. Because the instrument, this is something I didn't mention yet, but the instruments will be delivered in a few years, so much earlier than the launch and the discovery of the target. So the instrument will define a range of parameters in which they will be able to do the science.
Okay. So you're kind of building instrumentation for an object you don't know yet. So you have to make some assumptions on what kind of object it will be intercepting, so you can build the right instrument. So it's a lot of guesswork and
Yeah.
estimation and prediction, and we need to be a little bit lucky to make sure everything lines up.
Yeah, exactly. But the idea is that we don't have to be that lucky because we will have a lot of statistics. Because if it's true that LSST will find 1,000 per year, then it should be safe.
Are you going to see data from the Rubin before instruments have to be finalized?
Yes.
Okay, so great. So that should help.
Yeah. So the first flight is expected in a few months. So it's very
Yes, this year is months away.
yeah, it's months away. They just mounted the camera on at the telescope, the LSST count, which is in the World Guinness Record, I guess. It's American thing, so I'm not.
It's big.
Yeah, because
Yeah.
it's the biggest compact camera ever built. So it's impressive. So the first light means the first time it will be used to observe the night, but the survey will start next year. But still, 2026 still means that we have a couple years of possibility to access the data and see how it goes. And that's why I think, like, actually in 1 year from now, we will be able to see much more about the statistics of and the probability of get the right target.
Great. Like I want to tie this into this is more a speculative question. I'm going to tie it to another guest I had on this channel, which is Avi Loeb, who did a lot of research and writing about the Oumuamua. And I'm curious, like if there was a situation where your interceptor was in the Lagrange point, and we had the Rubin, and we saw something like a Oumuamua ahead of time. Like, did it come close enough, did it have enough of the characteristics that are in the envelope of let me call it your intercept envelope, that where it could have been possible if the committee deemed it was a worthy target to have done the flyby? Did it come roughly close enough for us to be able to do something like that?
So the first thing I want to say is that if something like that was in the option, no doubt we will go there. That's the top priority target.
What makes it top priority?
Oh, because an interstellar object, that's something that can tell us about protoplanetary disk. That's exactly what we want to do in this mission. We want to understand how planets are formed, how they evolved, and a piece of rock that comes from another system is one of these pristine objects. So it's going to tell a lot.
But what makes it more pristine than something from the Oort cloud? I'm trying to understand why that's more interstellar object is more interesting than something from the Oort cloud from our solar system.
It might. So the idea is that to be able to actually leave the gravitational field of the system which were formed, it should be really, very tightly linked gravitationally. So this means that it should be really one of the scattered pieces from the formation. So it should be unaltered in any way. But of course, even if it wasn't that more primordial than the Oort cloud comets, still, this is the only chance we will ever get to observe something from another solar system.
Another solar system. Okay, that itself makes it very interesting, because we're like we really have no clue on what things look like or what things are in other solar systems. So this is like a little piece from these other solar systems that
we have observation, we have clues. Mm-hmm. They are always taken far away. This is like
far away.
The opportunity to actually look at it.
See up close another solar system. Yeah, okay, I understand.
That would be really amazing. So, but we have low hopes for that to happen. So for Oumuamua, it was close enough. That's why the mission, our mission, so the Comet Interceptor mission, actually states that the target will be either an interstellar object or a comet. Okay, so we
Or comet.
hang
Okay.
that hope. Yeah, and so the the point is that it was a little bit too fast for us because the instrumentation that we are now designing put put a limit on the relative velocity between the spacecraft and the comet, and that basically is for safety reason, because you have to think that the comet is ejecting particles, okay, and this particle will have the same velocity because of physics, the same velocity of the comets. This means that they will hit the spacecraft at the relativity velocity of the comet spacecraft. So impact at more than 80 kilometers per second are extremely, extremely dangerous. They go through. they will put holes in the spacecraft. So we
Right.
want that. Yeah. So that's the point. So we have range, like you said, the envelope. It will be a little bit outside, but I mean we have such a low statistic. We only observed 2 of these interstellar visitors, so we have no clue what is the range of velocity they can have. So who knows?
So now, is the current project scope? It sounds like it's just one shot. Basically, we're getting this thing into the Lagrange point. We get to pick one target, and we're going to go for it. Does the current program have more? Is there another spacecraft in the works, or is it just kind of we have one shot?
No, at the moment this is it.
This is it. One. Yeah, I mean, it is one shot, right? Like literally one shot.
That's why ESA want to be sure that we are thinking very carefully about which target we want to go to. So
what would be great is to understand a little bit more, like how you grew up, and like, has this fascination always been with you, like, or did something spark this? Like, I'm very interested how you got into this, how you got on this path of becoming a scientist. Can you share a little bit about what created that spark?
Yeah, so I was fascinated by stars since I was little. I think I owe that to my father, my dad, who was always telling me about the name of stars, of the constellations, things like that. But it was more like a romantic fascination. So I like to be able to recognize the constellation in the sky, and looking at the star was all beautiful. But like when I was still in middle school, I wanted a microscope. So I was
not a microscope, not a telescope.
More, I mean, from the stars were like more romantic interest, and from the science part, I was more interested in biology, things like that. But then after high school, I had to decide what to do next, and because I studied literature, like in the high school, we have this kind of school in which you do Greek and Latin. Ancient Greek, ancient Latin, philosophy, literature, all this kind of thing. And very little math and very little physics. So after that, I was like very tired of things I couldn't really measure, or I couldn't put in a clear relationship of cause and effects. So I decided to go and study physics. It was like more like a rebel reaction to my previous studies. That's a real motivation. So there was a little crazy.
Basically, you felt like the other studies were too abstract, and you wanted something not as abstract.
Yeah, exactly.
And what was this? This is what I'm assuming it was in Italy, but kind of where you are now, or someplace else?
No, I studied in Italy. So I studied physics actually here close to my hometown for the bachelor, and then I moved to Rome to do the master. That was already, but I mean, since I started physics, I decided to study physics because I wanted to have a broader perspective. But then my interest for the sky and the stars, it just came back, and so already my final thesis for the bachelor was on the Milky Way, so on the galaxy. So I was sure I wanted to study stars. So I went to the university in Rome to do astrophysics. So I'm an astrophysicist. And then I did the PhD there. But after the first year, I got this opportunity to go to ESO in Munich. So I spent 2 years there.
What's ESO?
ESO is this European Southern Observatory. So it's also an European organization, but instead of coordinating a space observatory, it coordinates ground-based observatories, which are basically the VLT in Chile, which are the 4 big telescope in Cerro Paranal, which is not too far away from Cerro Pachón. And that is now building the EELT, the extremely large telescope, which will be this telescope with a diameter of 39 meters. It's already in construction, actually. So that's on Cerro Amazonas. So they are all there in the Chilean desert.
What you hope to discover in your wildest dreams? With Comet Interceptor, what do we hope to discover scientifically?
Yeah, I guess the great discovery will be to understand the origin of life on Earth. So again, to see if these kind of comets were actually the responsible for bringing organic compounds and water on the Earth. So that's the big question. But I mean, personally, there are also a lot of things I'd like to understand, and I plan to do that even before the mission, like with the Vera Rubin, when we will start to have much more observation of this comet, because it's impressive that we have been observing comets for so long. Like we have the first observation in the Babylonese thing, so it's impressive, but we still don't know exactly how they work. So we still don't understand the physical mechanism behind their evolution. We don't know the evolution when they are so far away. So we have observed them always so close by when they cross the water ice or just a little bit before. I think the record is for the Bernardinelli comet that was observed at 16 AU, so very far away. But with the Rubin, we will start to have many more of them. So we can really have a better understanding of what is the Oort cloud. And so for me, that would be already very interesting, trying to put together all these pieces of the puzzle of how planetary system works.
Fantastic. Well, I wish you the best of luck in these upcoming discoveries. Thank you so much for having this conversation with me. It's been illuminating. There's things I just learned about the Earth and its possible formation. So you've increased my understanding of our solar system and our home. Is there any other things you'd like to add to this conversation?
Not really, but I mean, if you have, just reach out again and